evening. Welcome to another lecture of Scientifically Speaking, an interactive online lecture series that connects world-renowned scientists to high school students and teachers. Today we'll be discussing the topic, the science of computing, an entry into a new world, with Professor Pankaj Jalote, who is a distinguished professor and the founding director of IIIT-Delhi. But before we move to the session, I would like to thank our guests who attended the previous lectures of Scientifically Speaking. Our 5 previous sessions have had over 36,000 registrations and 10,000 plus live attendees on Zoom and YouTube. The recordings for these sessions are on Ashoka's YouTube channel, the link to which is provided in the chat box. With that, I welcome our moderator for today, Mr. Shyam Vupuluri, who is a research associate at the R.N. Poddar School in Mumbai. Shyam is the recipient of the 2020 Albert Einstein Fellowship at Kabul and is an elected fellow of Royal Society of Arts. He's currently working as a research associate at the R.N. Poddar School and has a long-standing interest in foundation of sciences and philosophy. As an instigating editor, he has edited several highly interdisciplinary volumes published in Springer Verlag in order to disseminate and discuss issues underlining the foundation of sciences. A very warm welcome to you, Shyam. Kindly take over from here and introduce our speaker for the day.
Thank you, Vikram. It is indeed a great pleasure to have Professor Pankaj Jalote with us this evening. Let me say a few words of introduction before we hear his intriguing talk. Professor Pankaj Jalote is currently a distinguished professor of computer science and was the founding director of IIIT-Delhi. Earlier, he has also been an assistant professor at University of Maryland, professor and head of computer science department at IIT Kanpur, and chair professor at IIT-Delhi. He has also been a vice president at Infosys, visiting researcher at Microsoft, interim vice chancellor of Delhi Technological University. He is an author of 5 books, some of which have been translated in Chinese, Japanese, Korean, and so on. And the Indian edition of his text on software engineering was adjudged the best-selling book by the publisher. He has served on the editorial boards of IEEE Transaction on Software Engineering, International Journal on Computer Software, Empirical Software Engineering, and IEEE Transaction on Services Computing. He is also a fellow of IEEE and INAE. Over to you, Professor Pankaj.
Okay. Good evening, everyone. Thank you for joining. Let me share my screen, and then we can get started. Okay, so for about 25 minutes or so, I'm going to talk a little bit about science of computing. So this is not going to talk about programming, software, new programming language or anything like that. We are going to just discuss a little bit as to what computing is, what is its limits, etc. But let me start. So, since most of you are school teachers or school students, that's what I understand. So we know that in schools we teach physics. Physics helps us understand the physical world. We study chemistry, how chemicals work. Biology, about how life works. Social sciences helps us understand society, organization, people, right? Humanities help us understand ourselves, our humanity, spirituality, etc. Right? So because we need to understand the world we are in, schools teach these things to our students. The question I have is, why do we teach math? And why do we learn? Okay? Math is completely abstract. And it does not in any way explain any aspect of the real world. Okay? So I would have liked to interact, but we don't have that given the number of people. I'll give you 1 minute to just think about it. Why do we teach algebra, geometry, calculus? Right? We understand why to teach physics, sociology, history. Why maths? Okay, something to think about But here is my take, or here is one way of looking at math. Maths is a fundamental modeling and problem solving tool. It's not explaining anything by itself. What do? You model a problem or a phenomenon as a mathematical formulation. Then you solve it using mathematical techniques. Then you interpret the results in the real world, right? So Newton's laws, convert it into equations, which is the mathematical formulation. Then you can solve the equation. And once you have solved the equation, then you can translate the result back into the real world, right? So that's what maths is for. And that's what I show here. From the real world, you get to the mathematical model. From the mathematical model, and that mathematical model is easy. You can just work on paper and pencil and solve the problem, while the real world problem is very, very complex. And with mathematical solution, you go and you have found the solution to the real world problem. You, of course, have to interpret the mathematical answer to the real world. That is again back to you. Okay? So we use math to solve it. So why do we use math? Is because, first of all, it's very efficient. It's far quicker. Solutions can be more accurate. And there are some problems which you just cannot solve without mathematics. And there's a whole new insights possible. So Einstein's theory cannot be possible without math. And of course, all of us know Newton's laws. These are all mathematical equations, right? So they help us give very accurate models of the real world. So computing is also a tool for problem solving. Okay, that's the only reason I brought maths. Even with maths, not all problems can be modeled and solved mathematically. We know that. Computing provides yet another way to solve many of these problems. Sometimes that's the only practical way to solve the problem. I'll explain a little bit more about it in a moment. But keep in mind, like math, it's a problem-solving tool. It in itself doesn't do anything. You have to bring the problem, model it as computing. So computing adds, just like math added a new type of abstract thinking, variables, equations, matrices, right? It provided a vocabulary of abstract thinking. Similarly, computing provides a new type of abstract thinking, which relates to algorithms, right? So with algorithmic thinking, which is also an abstract thinking method, which algorithmic thinking and constructs, solution for many hard problems could be formulated. So like math, it provides a new vocabulary to formulate problems and solutions. The science of computing, therefore, is frameworks for solving problems using computing machines. Right? Keep in mind that when we're talking computing, underneath there is a computing machine. Whatever you do, it finally has to be executed on a computing machine. And all these frameworks of how can we make this computing machine a good problem-solving tool is what science of computing is about. So let's see, what are key elements of this science of computing? So I'm going to assume that you have a sense of what algorithms is. An algorithm is like a recipe. How do you solve a problem? It gives you a sequence of steps. Just like for cooking, it gives you a sequence of things to do. Algorithms is also a sequence of steps in a certain way. So algorithms for solving a problem is, of course, the first thing. If you're going to model the problem, just like in math, you have to find equations which will model the real world. Here, algorithms for solving a problem, you have to first formulate those algorithms, right? So that naturally, the science of computing has to talk about how do we formulate algorithms for solving problems. But algorithms in themselves don't solve problems. They are just something on a piece of paper. You write down something on a piece of paper. The algorithms have to be expressed in precise programming languages. That's something many of us understand. Many of us would have written some programs. So you write express these algorithms in programming language. And this provides another dimension of the computing sciences, programming languages, and a host of issues around programming languages. How do you express the algorithm in a very precise programming language? But the programming language also does not solve the problem. It has to be executed. And programming language itself, most machines can't execute programming languages themselves. So the programming language, the programs written in the programming language have to be translated into a format which the machine can execute, which the machine can understand. So there is one aspect of science of computing is how do you translate a program formally expressed in a programming language into an executable. And then, of course, that has to be executed on the machine, but machine needs some support there, from where do you execute, where do you put out the output, where do you take the input from, all those have to be done, and therefore the systems to execute the executables become also part of the science of computing. And of course, overarching all this is there is a whole theory around what can be computed, what cannot be computed, etc., etc. So there is a theoretical framework which goes around all of this. So to see it pictorially in some ways, the key aspects of the science of computing you can look at starts from algorithms to solve problems, right? And there is all various aspects, complexity analysis, how do you verify algorithms, how do you make sure that the algorithm is correct? How complex is it? But the algorithm has to be translated to an application program, which is written in a programming language. So there is whole area of programming languages, tools, methods. There's literally hundreds of programming languages. And I don't mean it as a hyperbole. Actually, there are a couple of hundred programming languages. And then, of course, programming languages, then you have to prove the program correct. There are various tools there. And then this program written in the programming language has to be translated into code that machine can understand. And that brings in the whole area of compilers, interpreters, code checkers. So that's a whole area in computer science, which is trying to go in this stack of problem solving. And then this has to be executed, and you need a range of software now to execute the program. Operating systems are needed, linkers, loaders. I mean, we know the operating systems, whether it's Mac OS, Windows OS, right? When you double click some application, it has to be run and the operating system takes care of it. So if you look at the computing itself, unlike math, we just provided the formulation and then people have to work at it. The science of computing has to bring in all these aspects. Algorithm is thinking tool, writing programs in a certain language, and therefore you need programming languages, and you need the science of computing has to handle this. Then you need translators. Science of computing has to handle this. And then system software is needed to run these things. Okay. So it all starts from algorithm, then comes down to statements which the computer can execute, right? And then the interesting thing, which some of you would know, so to solve a problem as a computing problem, you need to specify the computing instructions, right? The recipe. Do this, do this, do this, do this. But what is this? What do you tell the computer to do? Of course, you can't just tell the computer sing a song or, hey, go and solve this equation, right? There is only certain things that the computer or the computing machine will understand. Okay. As it turns out, interestingly, very few, these 4 types of instructions is all you need to compute anything that can be computed. Okay, let me again restate it. Anything that can be computed by just these 4 types of statements. Assignment, X gets Y, X gets 5, X gets 25. Sequence of instructions, do this, and this, then this, then this, then this. Conditional execution if x is greater than 5, do this. If x is greater than 0, do this. If x is less than 0, do something else. Conditional execution, that is, you execute a statement based on certain condition. And iteration is repeat this thing multiple times. Just these 4 statements can do everything that is computable. So therefore, what you need is a machine underlying which can execute these 4 statements. So if you have a machine that can execute these 4 types of statements, then you can build on top of it. You can write, program in a higher level language, which will convert it to this, and then all those other portions. So at the lowest level, at the machine level, you need a machine, computing machine, that can do these 4 things. Okay. So the computing machines, of course, all that we have, all have this power to do it. And of course, now, and then they add more bells and whistles to make life easier, but this is the heart of it. And then the different programming languages and tools that we know, whether it's Java or Python or C++ or what have you, those are only to make life easier for people who are solving problems using computing. Okay? But computing itself boils down to these 4. That's what a machine has to do. Okay, so given that the power of computing lies in those 4 types of statements, and then higher forms of it, which we can then comfortably write in programming languages, that's the power. So with that power, actually computing can solve many hard problems. Okay. Of course, all of us know a lot of them. We are using computers all the time. But let me give you some examples of the kinds of problems that computing can solve. Not computers themselves, this whole stack that I talked about, algorithms converted to program, converted to machine language, converted to execution. So for example, if you have to go from A, let's say A is Allahabad, to B is Bangalore, how do you go there? There literally, actually, just these 2, Allahabad and Bangalore, there would be literally millions of possibilities. So what's the shortest path? How do you think Google Maps computes it? Google Maps tell you, and all of us rely on it. So the Google Maps is running an algorithm called shortest path algorithm, and it in whatever language Google Map is coded in, probably Python. So it selects out of these millions of possibilities quite efficiently the shortest path, the best path. Okay, so this is a problem which maths can't solve. Or the mathematical formulation, you can't just solve it by mathematical formulation equations and all that. Kidney exchange is another problem where actually there are kidney exchanges running in developed world, largely relying on algorithms, right? This is part of a broader matching problem, right? So somebody needs a kidney, has a donor, but the kidney doesn't match. But there's another person who has a donor, and if they exchange, then things can work out. And of course, you can make this bigger chain and all that, right? So there's many algorithmic solutions for kidney exchange. There's similarly something called a stable marriage problem, which, something similar to that. Whether a large number is prime, right? A small number is prime, we can run it ourselves. By the way, what the method that we use for finding whether a number is prime or not is also we are using algorithmic technique. It's only that the computing machine for these small numbers, when we do it, is us, not a machine. Okay? But we are using computing approach. There isn't an equation that tells us if the number is prime, right? So there are many methods for primality testing, and all are computational. Large number is a prime or not, only computation can work there. Optimizing something, right? All of us would have learned something about minimize this, maximize this. Now there's some problems you can do by mathematics. Model it as an equation, differentiate it, set it to 0, optimize, solve it. But there's a huge range of problems you can't solve in the mathematical manner. So there is a range of optimization algorithms that will optimize. And of course, some of you may know, whether it's physics or chemistry or lots of things that happen in real world can be modeled as partial differential equations. Really solving them mathematically is very, very hard. Very few things you can solve mathematically. They're almost inevitably solved numerically, which is computationally. Okay, there is a range of them. I gave you just a few. But computing is not the answer for everything. It cannot solve all the problems, and there are some problems it can't solve efficiently. Okay? So first of all, there are some problems which computing just cannot solve, right? And remember what we talked about computing? Computing is that machine which has those 4 types of instructions. And of course, built upon top, we have, using those 4 instructions, certain program. Program was an output, was based on an algorithm, etc. Some problems which this computing cannot solve. And here is one. For example, given an arbitrary program, many of us would have written programs, there isn't any program that will take an arbitrary program and tell whether this program will halt or not. Okay, maybe hard for some of you. But if you have to algorithmically solve this problem, given arbitrary program, please tell me whether this program will halt or not. This is the problem statement. Can you write a program to solve this? No, you cannot. Period. You cannot solve this problem. Okay. Similarly, given a polynomial equation with integer coefficients, and a finite number of integer variables. That is, the variables can take only integer values, not real values. Does this equation have a solution? No, there isn't any algorithm or program which, given arbitrary equation of this kind, will tell you whether it has a solution. Okay, arbitrary equation of this kind. Okay? So there are some problems, and there is a host of problems. You can search for problems that computers can't solve, or undecidable problems, they're called. So you search for it, you'll find a whole bunch of them. Now there are problems that will take a long time, even with the fastest computers, if the size of problem is very large. Small size, yes, you can solve. Okay, one of them is what is called traveling salesman problem. And the idea here is there is a salesman who leaves his home and has to go to A, B, C, D, X, Y, 1, 2, 3, 4, many different places, and finally come back home. And he wants to do this circuit. Of course, he wants to travel the least. How does he reach all these thousands of points where he has to go in the minimum time or a minimum distance? Okay, small problem, computers can solve. But if it becomes very big problem, millions of points, etc., even the fastest computers can't solve them. Okay? Or they can solve it, but the time it will take could be years. And I'm talking years, right? If you make it large enough, it can actually take years. Okay? Your computer may die before that. Okay? So bin packing is another problem of this category, where you have packets of different sizes, and you want to put them in bins, and you want to minimize the number of bins that are needed to pack all of them. Okay. Now you may think, of course, I'm given 5 bins and 50 packets, I can probably figure it out. But again, you put it in millions. There isn't an efficient way to solve it. There is an algorithm to solve it, unlike the other ones where I said where no algorithm exists. Here, there is an algorithm to solve it. There are algorithms to solve it, but they are inefficient. In that computing machine you put for a large problem, it will take a long, long time. Many of them can take years. I mean, depending on how large the problem is. So there is a large set of problems called NP-hard, and there is which just take a long time to solve, though there is algorithmic solution. It just takes a long time to solve. And by the way, for those who are interested, a subset of them is called NP-complete, which means if you can solve one of those problems, you can solve all of those problems. Okay? And while I'm not going to explain, P equals NP is the most famous unsolved computer science problem or math problem, if you will. Okay. So that's about so far, I have another 5 minutes left. So far, I've talked about computing only. The instructions you get and you compute something. Now comes data science, big data, machine learning and data science. It's a new paradigm which has emerged using the big data and the computational capability that we have. Now remember what I said in computing, you build a model, computational model, and then you solve it. In this model, machine learning model, in the machine learning approach, even the models themselves are built computationally. Okay, with the data guiding how the model is constructed and how the model is executed. Okay, so in computing only, you build the model and then you execute it. In machine learning, even the models themselves are built by the computer programs, and the building of the model is guided by the data. Okay, so it builds upon computational science by even building the models computationally, but needs huge amounts of data. Okay, so with this, computing sort of moves to a higher level of abstractions. Right? It's possible now only because both large data and large computing power are there. So it requires, of course, large amounts of data, but it also requires large computing power. Okay, so this is the new science, if you wish, beyond computing science, machine learning, and data science. So in the next couple of minutes, I just want to discuss with you that you can view all this in another way. Okay, so I've talked about computing science, its limits, what it can do, what it cannot do, and then with data added onto computing science, it just adds another dimension. Okay, another way to view these is in terms of the scientific paradigms, right? So it is said experimental science was the first science. It was there ever since humankind came. You experiment, you do some things, control some variables, learn from the experiment. That's how we learn. That's how we solve problems. And that has been there ever since humankind has been there. Then came theoretical science. What do you do here? You propose a hypothesis based on some conceptual models. Then you prove it either experimentally or some mathematically. And once proven, it becomes scientific knowledge. So Newton's laws, Einstein's theories, etc., these are all theoretical science. Now, theoretical science broadly has been there about 1,000 years, roughly, let us say. And it relies hugely on mathematics. The problem that the thing that I mentioned, you use the abstract world of mathematics to model and then explain things, and that gives you the theoretical science capability. Okay? Computing science is the third paradigm of solving problems, where you solve problems using computing. It also helps the other two paradigms, experimental and theoretical, handle additional class of problems, right? And it provides new ways to solve some of those solutions. This was developed in about last 100 years, broadly speaking, right? Computing science. Data with computing, that can be considered as the fourth paradigm. Okay, there are different ways people look at fourth paradigm. Fourth paradigm is a term that's used, but it provides new ways of solving problems which just data or just computing cannot provide. You have huge amounts of data, can't do much. Lots of computing, but no data, can't do this. Here, models are themselves built computationally. This is development of the last decade, right? So we have, ever since mankind, experimental science, maybe 1,000 years theoretical science, last 100 years computational science, And now, last decade or so, of course, the theoretical foundations of it came earlier, but last decade or so, this thing has become far more. Okay, so I'm almost done, last minute. So the summary, just to end, so computing is a problem-solving tool. It expands the scope of problems that we can solve. And there are many aspects of computing. I talked about theory, algorithms, languages, systems, etc. And all of them have a foundational machine which can execute those 4 types of instructions and some more. But there are limits to what computing can do. And there are also limits on what computing can do efficiently. So as I mentioned, computing can be viewed as the third paradigm after experimental and theoretical. And computing with big data, it provides a power which just computing does not have. And that's the fourth paradigm. Okay, I'm done with this. So I'm going to stop sharing my screen. And yes, please. I think it is over to you for Q&A, please. Shyam?
Yeah, thank you very much. It was a very wonderful talk. So the questions that you have received, I think they can be classified broadly into 4 categories. I mean, the questions that are directly related to this talk, questions that are directly related to the computer science as a whole, and some are quite interdisciplinary questions, and some are related to the career and other sort of advice that people are looking forward from you. So
I would say let's look at a few from each category.
Okay. So I think let's start with let's start with the notion of the halting problem that you have discussed. So so one of the questions that we have received is that if the programs and the algorithms that we write are deterministic, and if the substrate of computing it's also deterministic, where is the indeterminacy coming into the whole process, and why can't some computers predict when a program can terminate or not?
Okay, so first of all, it's not a prediction problem. All computing is finite because it's a sequence of instructions you're doing. So the question really is, first of all, now why the halting problem exists, I don't think I have the answer to that, right? I'm not too sure too many people have answers to it. But any paradigm or any method for solving a problem always has limits. And that's what I wanted to show. Computer science, we start thinking that, hey, look, we can put any problem to it and it will solve. So I'm telling you that there are problems for which you cannot even write a program to solve them. And that is the limit in computing. Now, why that limit exists, I don't know. Why is the speed of light sort of the maximum? I wouldn't know that. But I guess this is a question, maybe I'll check with some theoretical people, but I don't think there's answer to this.
Okay. So the next question that we have is related to the artificial intelligence. So we have a question that says that there will be a revolution that is going to happen in the field of artificial intelligence, which increases productivity on a huge scale and of course cuts the labor. So however, in a country like India with a huge labor force, will it be beneficial, or how does one deal about the loss of the labor?
Okay, so there is, so it's not about prediction because I don't think anybody can predict, but one line of thought in all of these is this, that look, the past has shown, now whether the future would go like past is not known. When new technologies come, disruptions come, like AI, when disruptions come, no doubt a whole range of jobs will disappear. No doubt about that. But it's also known that the disruption, which is also a technology, creates a set of new jobs, right? So when word processor came, the typist went away. But then the new set of things came, people were working on Excel and so on and so forth. So we know that for sure. So that's what is hope. Now, what it means for India, perhaps is that we may find, and that's already happening, that a lot of work that Indian IT companies do are now also tying to managing the data, writing models, etc., etc.
So another question that we have is something related to the machine learning. So the question is that why is it that the case that machine learning always requires like large amount of data? Why can't it be like a small infant with a very normal and a very limited set of algorithms? Why can't, like, just as an infant with a given genetic endowment, why can't a computer also can do with a very limited set of algorithms and learn the world around it and structure the world around it?
Okay. So let's take the analogy of the infant. Now, the infant is also using data. We talk to the infant, that's how the infant learns how to speak. The infant sees, that's why, okay, that's a dog, that's a cat. The infant builds. Actually, in fact, by the way, machine learning, many of the people, the neural network model is really tried to model the brain, right? But please let us be clear, we also learn from data. Except when we are applying mathematics, etc., etc. So when we are evolved, but certainly infant and younger people. So they are trying to sort of mimic that. In fact, to a person, it takes years to learn often, and hopefully, I mean, they're assuming that the compute power can do this. But there is nothing intrinsic. You can't learn completely on your own. You have to bring in certain data. However, there are some ways where not the data, but you can codify certain rules. So it doesn't need data to learn, but you have put all the learning in the rules. But then that's your learning on into the program. So, but for the program to itself compute, determine the rules, it will need data.
So another question that we have is that a lot of students want to hear you speak about the quantum computing and the quantum internet.
Okay, so I really don't know much about it, but let me tell you this. As I mentioned, the computing model we had, what is the computer underneath? 4 instructions. Sequence, assignment, sequence, conditional, iteration, right? That's the model of the computer. I'm giving it in a simpler way. Now, these models were first abstractly determined. Turing is a famous guy who stated all this. And then they were implemented by transistors, etc., etc. And then a couple of 100 years ago, there were Babbage computing by mechanical these things, but let's not worry about that. So this was the model which is implemented in our machines, right? The processor, the Intel processor we have, etc. Now, what quantum computing is doing, it's saying this is not the model of computing. It's not assignment, sequence, conditional, iteration. It is going and looking at a very different model of computing, and they have derived a model of computing where you work, instead of this computing that we talked about, works on bits, ones and zeros, everything comes down to ones and zeros. That works on quantum bits. So like using quantum physics, where it needn't be 1 or 0, but something in between. The challenge there is, can you build a machine to implement this? You see, this was a machine, we said, we can solve a lot of it, and then out came transistor, and the transistor and using the transistor, we were able to build the machine. Now we have to build that machine. And the recent advances seem to suggest that that machine also can be built and are being built, right? Now, if those machines which will implement that model of computing, not simulate using computer, then you're down, then you are limited to this computer's power, but actually execute in that manner, then we will see a different model of computing, and that model will have different power, more or less, will have different power, and will have different limits, right? So math had its power and its limits. Computing of the kind that I mentioned has its power, has its limit. The computing, the new model which quantum is talking about, which I know very little about, but that model, which is not ones and zeros, but quantum bits, is a different model which will have its power, which has its power, but will also have its limits. But we still have to see whether a machine can actually be realized to execute it, which is happening. So then we'll see that, just like we saw this thing, we'll understand more of it.
So another question, a little bit interdisciplinary, is related a little bit to the physics. So somebody asked, why do we study the notion of entropy in information technology, and what is its application? I mean,
why do we study entropy in information technology?
yeah, I mean, in computer science as a whole. Maybe she meant like that. I mean, maybe she's referring to Shannon.
I don't know what concept of entropy the
I mean,
person.
Shannon's entropy and.
Oh, okay.
I think she's referring to that.
Okay, if that's what they see. Shannon's theorem again. That's something I just brought. So Shannon was talking about communication. You know, when you go from when you want to send information, then there is a whole area of information theory, which talks about, you represent the information in a certain way, then you transmit it. So what can you transmit? How can you transmit this much of information in, little things? So that's compression and all that. So there's a whole area of information theory where these concepts of entropy, etc., come in, which are not the same concept of entropy which you see in thermodynamics, which is talking about the physical world, the chaos is increasing. Okay, so don't confuse the two entropies.
So the another interesting question is that if AI becomes quite advanced and if it is given full freedom, I mean, I think it's pointing out to the Isaac Asimov's hypothetical thing. Could it become evil?
Could it become evil? Okay, so I'm not. First of all, I'm not a very unfortunately, not a sci-fi reader. But as of now, as I said, so as of now, I think it is sort of limited in scope to what models it can learn and then what it can predict. It's really a prediction engine, right? To start becoming evil, of course, which is also happening, you'll have to also make it enable to do things in the world, right? Which has also happened. There are robots and you can do things, but I think it is still under the control of a program. And as I said, the model is also being computed programmatically. It's not something happening on its own. But yeah, what is coming out is sometimes these models show interesting insights which you didn't know from before. But that's okay. So I don't believe that it can come to the kind of robots we see in some movies. Yeah, but just to say, you can program such robots. Okay, so I'm not saying that you cannot make. See, you can make machines which will do evil things. That's possible. But the question, I guess, is can machines become so that you can't control them? That I don't think is possible. It's my view.
So the other question that we have is, what is the role of computing? I mean, I think broadly in chemistry and especially in stereochemistry and its application to model 3D molecules.
Okay. Unfortunately, I'll have to pass this question. Even in my class, even in my first year in engineering, I was poor in chemistry, so I wouldn't know. But I'm sure you would know of if you use math in chemistry, you can find places where you can use this thing. Certainly, I'm sure chemical reactions, etc. There would be ways to model them as differential equations, and if you can model them as differential equations, then it will need computing to solve it. But I'll defer this.
So we have another question. If I understood it correctly, so what he is trying to ask is, in olden days, people used to remember a lot of arithmetic calculations and all the tables by heart, and they used to do. There was no computers those days, and nowadays kids from childhood, they are given calculators and so on. So what is the difference? I mean, does this also affect their logical thinking, the role of memory and doing computation physically, if a person is purely dependent on computers from childhood to perform all arithmetic computations, would that affect his coding skills or his programmatic thinking or logical skills?
Okay. So let me tell you one answer that is generally given and then what I think. So just said, the kid plays with and they can do lots of things with your phone, which even I can't do, right? And they can do it. But the person who learned the tables, he couldn't have done it. So let's first understand the kids are learning different things today. Okay, so let's be clear. They are, in some sense, they have actually seen much more than kids before. They probably have much more neural networks, bigger neural networks, more complex neural networks in their brain than when we were kids, right? Okay. So it's a different style, different things of learning, different ways of learning. Now, where will it lead them to? That is an open question, right? Because there is psychological aspects of it. After all, will it mean that the person always is hooked to it? And the person, will it cause stress on the person all the time, anxiety, etc., and eyesight, is that, right? So those are things which are still there. But having said that, so people essentially believe that you are now doing different kinds of things. So you don't need to remember tables anymore. You don't need to remember some other mathematical thing because you can look it up. Now you can work with higher level constructs. Equations is that. Once even equations are known, then you go even higher level, right? So you work with higher level constructs, more creative and all that. So that's one thought, right? However, my personal belief is, now this is in the personal belief realm rather than, because I don't think any of this is really established. We have to see how it pans out. Okay, my belief is that some of these are basic skills, and I actually believe and have often advised people not to get into computing and all that very early in the game. Start thinking about ability to think rationally, think things out, look at numbers, look at abstractions, look at the world, etc., understand people, and start computing much later in the game, right? So I am of that view that all these things help you in your mind, in your neural network, you're building connections, etc. And connections of computing, which are based on computer science, can be built later. So you do, and therefore, they can be add-on. You don't have to sacrifice these to do that. And these provide some kinds of thinking. Perhaps it also helps you in empathy and human connections. So I would prefer it that way.
So the another question that we have is that what are some recent breakthrough or major developments that you have seen? I mean, maybe one or two of them that are quite challenging and that you would have expected to the result to be otherwise, but that got disproved, or some very recent advancement that really impressed you in the field of computers.
Okay, so I'll mention one which recently got the ACM prize as well. So I gave a simpler method, simple concept of machine learning where computing tied with data and then you can build models computationally. Right? There's an area of machine learning called reinforcement learning where you write a program and essentially, so for example, for game playing, right? So game playing earlier, you remember, it took years for people to write a program to beat good players in chess because they were hard coding rules and so on and so forth. But now there is this area of reinforcement learning where the computer program plays with other computer programs, or rather plays with a replica of itself. And each time it wins or loses, it keeps learning. Okay, and therefore they found that there was this. I've never played this game, but there's a game called Go, which this computer program was able to learn from scratch within a matter of days and actually beat the world champion. So this kind of, so in a certain class of problems, which earlier we thought will take a long time, lots of data to learn, now they found ways where computer is learning by just playing, and you're finding that out, right? And that got one of the highest awards in computing.
We have another career-related advice somebody is seeking from you. They are asking, how would a teacher or some instructor develop the computational thinking in students? Are there some good resources that you can suggest?
So, okay, if it's a school teacher, I'll assume it's a school teacher. So I've given a talk in some schools also. I think schools are often taking it very wrong. They're teaching computing in an incorrect manner. Improper manner, I think, right? See, computing is a tool for solving problems. And then there is whole, as I said, algorithm. And then after that, you have to write it in programs, and the program has to be debugged in programming language and so on and so forth, right? Now, this is what engineering students have to do. They have to learn how to write programs, debug it, make sure it's well. Algorithm is typically done by, also done by engineers. But now in school, what ought to be taught is not about the programming languages and the jings and bangs of the programming languages, which is a matter of detail. But what ought to be taught, just like in math, how do you use computing to solve problems? That's computational thinking, algorithms, etc., etc. So even if you can just stay at the algorithm level, and if you must use programming, which either use a very simple programming language. There is this Lego programming language, which I know teachers can't change it because CBSE guidelines, etc., etc. But if you must, then make the language a very small subset and say you can only use this. Don't, unfortunately, they're focusing on the language. Objects, classes, inheritance, this, that, they're teaching all kinds of stuff. While what ought to be thinking is like math, how do you solve this problem? Tell me the algorithm, tell me the recipe. And you help the student express it in a proper language construct, simple construct. So I would say, and there is, by the way, resources, then look at computational thinking. There is some things of that. And I'm sure if you look at the curriculum of universities outside, I'm sure you would find it, right? I've not looked at it at a school level. I've not looked at it much.
Okay, so I think we can just take one last question and then before we close the session. So one of the questions that we have received is that the usage of the data by computer scientists and everybody is increasing by the day. So will we have some sort of data crisis in the future? And if we have data crisis in the future, how can that be handled? Like just like any other renewable source of this thing, a non-renewable source.
Okay. So I think the person, so actually data got generated not because of computing. How is data getting generated today, right? First of all, our phones have multiple sensors. So in fact, all the data about the real world is today coming by sensors. So you have camera. Camera is a sensor which takes a megapixel, a 10 megapixel picture, and which is data. And we have sensors. We go where we know our coordinates and so on. So a lot of data is most of the data is getting generated by sensors, right? You have biomarkers, you have gene, etc. These are all things. Then you have telescopes in the sky which are getting all this data there. So the data is, and when you consume the data doesn't get, when you consume it doesn't mean that it goes away. The data still remains. You consume it in your algorithm, you use it, but that data is still there. So somebody else can also write it. So the data will always keep increasing. It cannot decrease. It will just keep increasing. And the way we are putting sensors everywhere, I mean, every click of this thing, every place we have this thing. So the data is actually increasing far more rapidly than one had ever imagined. So it's not about the data crisis. I think we are swimming in data. The question is, how do you make sense of the data? And in fact, now there are challenges coming because the data is revealing way too much about people. So the challenges are now coming in the other way. There's too much data about myself. So there's privacy concerns. People know what I like, what I don't like, where I travel, they know so much about. So the challenge is coming about the data is in terms of privacy and other concerns, not about the volume of data.
Okay, so that's wonderful. Speaking to you, I'm sure our students have benefited from you, and I think I'll hand it over to Vikram.
Right. So I'll stop my video and mute.
Thank you, Professor Jalote and Shyam, for a wonderful session. There were a lot of learnings to take back, and I'm sure our audience enjoyed being part of the talk. Professor, we would love to have you back on Scientifically Speaking soon. I would also like to thank the organizing committee. 14 distinguished educators from schools across India have helped us put the series together. Without their continued support and feedback, the series would not have been possible. I would also request our participants to take a minute to fill our feedback form, the link to which is provided in the chat box. We have a fantastic session coming up on October 6th. The topic for the session is Selling Planet Earth, Repurposing Science Communications for Sustainable Human Well-Being by Professor Ian Stewart. Professor Stewart is the Professor of Geoscience Communication and Director of Sustainable Earth Institute at the University of Plymouth. He's also a visiting Professor of Environmental Studies at Ashoka University. The registration link for this session is also available in the chat box. Now, taking a short break from science, we would also like to invite our guests to join a webinar on performing arts at Ashoka University on Friday, 25th September at 5 p.m. This session will be delivered by Professor Justin McCarthy, who is the Director of Performing Arts at Ashoka. The link is there in the chat box. I would also like to inform all our audience that our applications for the first round of undergraduate admissions for the batch of 2021 will open on 14th October. For more information on the process, timelines, and requirements, please visit our website www.ashoka.edu.in or write to us at apply@ashoka.edu.in or call us at the number shown on screen. See you on October 6th at 7 p.m. Take care and please stay safe.